Isang magandang araw sa inyong lahat. Sa videong ito ay magsasolve tayo ng isang problem tungkol sa isang vapor compression cycle. This time, gumagamit ng internal heat exchanger. Basahin muna natin ang ating problem. So we have an R134A vapor compression system operating at 400 kilopascals, which is basically equal to 0.4 megapascal and 1 megapascal. It is using an internal heat exchanger for superheating and subcooling. The system has a degree of superheating of 5 degrees Celsius and an internal heat exchanger with a 100% heat transfer efficiency. The compressor efficiency is 75%. Determine the refrigerating effect and the COP of the system. So, bago natin simulan ang pag-solve ng problem na ito, alam natin na ito ang schematic diagram ng iyong vapor compression system with superheating and subcooling using an internal heat exchanger. So, ang gagawin natin dito, ilagyan muna natin ng labels yung bawat state points. So, at the outlet of the evaporator, we have our state 1. And we know that this is saturated vapor here. We are going to superheat it in the superheating line of the internal heat exchanger. Paglabas niya, we have state number 2. Ito ay superheated na. After that, it undergoes compression. So, we have state 3 at the outlet of the compressor and state 4 at the outlet of the condenser. Next, in the subcooling line of your internal heat exchanger, the outlet of that would be state 5. And finally, at the outlet of the expansion valve or the inlet of the evaporator, we have state 6. So, let us now draw our pH diagram. Sabi natin, meron tayong operating pressure na 400 kilopascals at 1 megapascal. Basically, 400 kilopascals is your evaporator pressure. So, we have 0.4 MPa here. This is the pressure axis and this is the enthalpy axis. And we have 1 megapascal as the condenser pressure. Inspect muna natin yung given bago tayo mag-proceed. Sabi dito, we have a degree of superheating that is equal to 5 degrees Celsius. So, basically, tawagin natin siyang delta T SH is equal to 5 degrees Celsius. Ano yung degree of superheating? The degree of superheating will help us in order to define state 2. Delta TSH is basically the difference between the temperature of state 2 and the temperature of state 1. So, basically, this is T2 minus T1 is 5 degrees Celsius. So now we have a heat transfer efficiency that is 100%. So remember in this part over here, nagkakaroon ng heat transfer. So the heat transfer efficiency here is 100%. That's a good news for us. So eta HX is gonna be 100%. And meanwhile, the compressor efficiency, it's also given, and it's gonna be equal to 75%. Ano ang pinapahanap sa ating problem? We have the refrigerating effect and the COP of the system. So we know that the refrigerating effect is basically given by the change in enthalpy in the evaporator. So we have RE is equal to H1 minus H6 because we have state 1 over here and state 6 over here. And the COP is going to be equal to the refrigerating capacity divided by the compressor work. So we have the mass flow multiplied by H1 minus H6 divided by the compressor work would be H3 minus H2. So we have M dot multiplied by H3 minus H2. So, alam natin na yung mass flows dito sa evaporator at sa compressor ay magkapareha. So, they will just cancel each other out. So, it's a matter of solving for these states. State 1, 2, 3, and 6. Okay, let us draw the pH diagram before moving forward. We know that at state 1, it is a saturated vapor. So, we have somewhere here. And as it goes on state 2, alam natin magiging superheated vapor siya at the same pressure. Because we assume that heat exchangers have pressure drops of 0. Next, state 3S will be somewhere here because it is an isentropic compression. But we know that the actual compressor outlet would be somewhere here. So, let us connect these two first. Nakalimutan na siya i-connect kanina. And let's connect points 2 to 3. So, we have here. Next, 3 to 4 would be an isobaric heat rejection, and we have an assumption that the outlet of the condenser is saturated liquid, so it will have something that looks like this, and the process goes from 3 to 4. Next, we have subcooling over here, and kung ano man yung heat na nire-reject nitong part na ito ay inaabsorb nung superheating. So we have 4 to 5 goes to the subcooled region. Again, this is going to be a horizontal line because we assume that there's no pressure drop. And then finally, it goes vertically downward somewhere here, kung saan meron tayong state 6. And in order to close the loop, we have an isobaric heat rejection from state 6 to state 1. Let's now solve for the different states in this problem. We have state 1, and sabi natin sa state 1, ang quality dito sa evaporator outlet is equal to 1 because it is saturated vapor. Also, it has a saturation pressure of 0.4 megapascals. Evidently, X1 is 1 and P1 is 0.4 MPa. We can say that H1 is basically equal to Hg, which is the vapor enthalpy at 0.4 megapascals. In this case, we don't need to solve for the entropy. Bakit? Kasi kinakailangan lang naman natin yung entropy kapag meron tayong isentropic compression na kasunod or isentropic expansion also. But in this case, in order to jump to state 2 from state 1, ang kailangan natin ay temperature. Bakit? Kasi given yung ating degree superheating dito. So that is the purpose of our degree superheat. Okay, so instead of solving for the entropy, let's solve for the temperature instead. It's a matter of consulting our thermodynamic tables. We have 0.4 megapascals. The saturated vapor enthalpy is 403.80. Samantalang ang temperature ay 8.94. So let us copy those values. Okay, so let us move forward to state 2. So, ang alam natin sa state 2, based on our equation a while ago, T2 minus T1 is equal to 5 degrees Celsius. We know that this is 8.94. So, T2 minus 8.94 is equal to 5. Therefore, T2 is equal to 13.94 degrees Celsius. Also, the pressure at state 2, if we are going to inspect our pH diagram, is still going to be 0.4 megapascals. Now, how are we going to proceed with the problem? We already know the temperature and the pressure at state 2, so in other words, we can now fully define the state. And ang susunod na state natin ay 3S, so perhaps we need to solve for the enthalpy and the entropy, and that can only be aided if we interpolate. So let's construct the interpolation table. At pressure that is equal to 0.4 megapascals, we have our temperature here, we have our enthalpy somewhere here, and finally we have our entropy somewhere here. So let's go to our superheated tables. We have 0.4 megapascals, 13.94 is somewhere in between 10 degrees Celsius and 20 degrees Celsius. So let's just copy the corresponding enthalpies and entropies in this table. Okay, so let's just place a temperature of 13.94 degrees Celsius over here and interpolate for the enthalpies and the entropies that we need. So whatever we get here is going to be our H2, and whatever we have here is going to be our S2. So let's just use our calculator in order to solve for this. Again, press setup, go to statistics, and we are concerned with two variable table. So, sabihin natin si temperature natin yung mga X, at in the meantime, yung mga Y natin ay si enthalpy. So, let us just input these values. And then, type 13.94. And we know that the temperatures are the X values and the enthalpies are the Y values. So, let's solve for the Y values. Press Option, go down, go to regression, and press number 5 for the Y coordinate. So we have 408.41268 as the enthalpy at state 2. Next, we can go to Option, press Data, and replace all the enthalpy values with the entropy values. So let's just type them all together. Again, type in 13.94, and this time solve for the y-coordinate, which in this case is the entropy. Go to Option, go down, press Regression, press number 5. So we have 1.738908 as the entropy. You don't need to copy everything. Okay? Pwede kayo mag-truncate sa, sabi natin 1.74, but I just want to be as accurate as possible. So let's move forward by solving the state 3s. We know that the entropy here, S3s, is going to be equal to entropy at 1.738908 kilojoules per kilogram Kelvin. And then we know that the pressure here at state 3s is also the condenser pressure. You can take a look at your pH diagram and see that it is indeed 1 megapascal. So what do we do next here? We need to solve H3s because our strategy is to use this and the compressor efficiency formula as well, which is this, which signifies that this is your ideal work and this is your actual work. So let's now solve H3s. How do we do that? We're gonna do another set of interpolation using the superheated region, this time at a pressure of 1 megapascal. So let's create our interpolation table. We have our entropy as our known, and ang unknown natin ay yung enthalpy kasi si H3s nga yung ating hinahanap. So at 1 megapascal, our entropy that is equal to 1.73 so on appears to be somewhere in between these two values. So 1.7139 and 1.7482. So kakopyahin lang natin ito kasama yung kanilang corresponding enthalpies which are around 420 and 431. And finally, we write down 1.738908 over here, our entropy that we are looking for the corresponding enthalpy of. So whatever we get here is going to be our H3s. So take note na itong value na to, dapat nasa pagitan na siya nitong dalawang ito. And if that is the case, we will also expect na kung naman yung value nitong enthalpy na masasolve natin ay nasa pagitan din nitong dalawang ito. So let's just use our calculator to solve this one. So I'll just type everything in the data table. Then press AC. The data will be stored. Don't worry. Type in the entropy at state 3s. And then press Option, go down, go to Regression, and then select Y hat. Again, this means that we are getting the y-coordinate corresponding to the x-coordinate, given that the x-coordinates are the entropies and the y-coordinates are the enthalpies. So we have 427.9517. Okay, our next step would be solving for H3 because we already know this H2 from the previous step that we had. H3s, itong kakatapos lang natin, alam na rin natin siya. Eta C is given, which is 0.75, and we can now use our calculator to solve for H3. So let us just input the values first. Let's use our calculator. Remember the technique, shift solve. Press shift, hit solve, and then input a relatively larger number. So sabihin natin mas malaki dapat sa 427, no? So mga 440. And it will give you an answer of H3 that is equal to 434.46. Okay, let us now solve state 4. State 4 is relatively easy. Bakit? Kasi alam natin ng state 4 ay isang saturated liquid. So, let's write it down here. The quality at state 4 is just gonna be equal to 0. And the pressure at state 4, if we inspect our pH diagram, is just gonna be equal to 1 megapascal. So, malinaw na sa H4 ay equal lang kay HF at 1 megapascal, or basically the liquid enthalpy, the enthalpy of the saturated liquid at 1 megapascal. So, if we take a look at our refrigerant table, we have 1 megapascal here. Saturated liquid is around 255.44. Okay, so balik tayo sa ating schematic diagram at pH diagram. We already know this, and this. So how do we proceed with state 5? Remember, state 5 is a subcooled liquid and wala naman tayong values for subcooled liquid dyan sa ating thermodynamic table, although kaya natin siyang i-estimate. Discuss natin siya in our future videos. But for now, remember that in our internal heat exchanger, we have the following relationship. We have the eta Hx multiplied by the Q at subcooling. It's gonna be equal to Q at subheating. So in terms of enthalpies, we have eta Hx that is equal to, ang heat sa ating subcooling, we have H4 minus H5. This is going to be equal to H2 minus H1. But according to our problem, the heat transfer efficiency is 100%. So basically, this is just equal to 1. So we now proceed with inputting the enthalpies that we have. We have H4 is 255.44 minus H5, the one that we don't know yet. H2, based on our previous problem, is gonna be equal to 408, etc. And also H1 is 403.80. So we can now isolate H5, and again, we use the same technique, our calculator. Let's just solve it here. And then press Shift, Solve. So, siguro nasa malapit siya sa 250, no? Input natin 250. Press Enter, or press equals rather, and then press equals for another time. So yeah, our answer is 250.83. We already know these states, 1, 2, 3, 4, and 5. And state 6 is basically equal to, or rather the enthalpy at 6 is basically equal to the enthalpy at 5 because it is an isenthalpic process. We just have to recognize that H6 is also going to be equal to 250.82732. Finally, we can now solve for the refrigerating effect and the COP. So the refrigerating effect is just going to be equal to H1 minus H6, which are as follows. If we input this in our calculator, we have the following. So our refrigerating capacity is 152.97, or around 153. So let's just write a bit more accurate value. So sabi natin around 153 kilojoules per kilogram. When you report it, you can just use this. Pero gagamitin natin to for the calculation of COP para lang mas accurate. Next, COP is equal to H1 minus H6 divided by H3 minus H2. Okay? So we have H1 minus H6 is basically your refrigerating effect, 152.97268. divided by H3 minus H2, which are as follows. So, one last step before we end this problem, let's type everything in our calculator. And then hit enter. So, our COP is around 5.87. Okay, so that's it. So, if you have any questions, just comment down below. But I hope you learned something in this lecture video. Thank you for watching.